Okay, good morning to all of you. I welcomes to all in our lecture series on mechanics, that is your core paper 2, and we are discussing unit 4 topic is oscillations. This is our lecture number 12. In this lecture we have to start to discuss a new topic, that is forced oscillation. Last few classes we have been completed our damped harmonic oscillation. So today we are going to start the new topic, that is forced oscillation. So according to forced oscillation, generally we can say that when a body oscillates in the presence of a resistive medium, then oscillation gradually die down and finally the amplitude becomes zero. These oscillations are called damped oscillation. Whatever we have been studied in detail about mathematical derivations of damped harmonic oscillations, and 3 cases also we have been studied. So whenever the oscillations is going to stop after some times due to the resistive nature of the medium, then that will be called as the damped oscillation. But this damped oscillation can be maintained, can be continued, can be maintained provided there is application of external periodic force having a frequency not equal to the natural frequency of the body. As a result, the body after some times oscillates with frequency of external force, or that is called the driving force. Such oscillations of the body are called forced harmonic oscillations. So whatever I studied or whatever I written, that I am going to give you an example from which you can understand exactly this, what we mean by the so-called forced oscillation. Okay. See, this is a oscillator. Okay, and it's suppose this line is the mean position, and it is at t equal to 0, it is at rest at the mean position. So if I dragged somewhat distance and I am going to leave, then it will oscillate, starts to oscillate. But due to the air resistance, you can see its amplitude is gradually decreases, and at last you can found that it's going to be rest at the mean position. Okay, but and this is nothing but so-called your damped harmonic oscillation. But this damped oscillation, whatever I written in the note, you can see that but this damped oscillation can be maintained provided there is application of external periodic force. External periodic force means with a particular frequency. If I am going to give, see, I am going to put, suppose this is your oscillation without any force, and due to the air resistance it is going to be stop after some time. But if I am going to give a periodic force from the outside, just see, I given a periodic force, you just watch my hand, a continuous, periodically I am giving a force. What will happen? Initially this oscillator not going to be match the frequency with this applied frequency of this applied force, externally applied force. Externally applied force is a periodic, means a force is going to be applied on this oscillator after a particular time. So and that the frequency of this periodic application of force is different to the frequency of this oscillator. So what will happen? That means this frequency and this frequency, the applied force frequency and this frequency is not going to be match initially. Okay, you can see this is one oscillation, one having one type of it's a frequency. I am giving another frequency. What will happen? First this oscillator is not going to obey with applied force frequency, but after some times it will oscillate with frequency of applied force. So initially the oscillator oscillating its own natural frequency, but whenever we are going to apply a force from externally, after some times the oscillator is going to oscillate with the frequency of applied force. That is called as your forced oscillation. Okay. So I hope with that example you have been understood whatever I written over here. Okay. What I written, I am reading, you just watch. But this damped oscillation can be maintained provided there is application of external periodic force having a frequency not equal to the natural frequency of the body. As a result, the body after sometimes oscillate with frequency of external force. The external force also called as driving force, which is driving the oscillator. Such oscillation of the body are called as forced harmonic oscillation. Okay. Now we have to go for the mathematical derivations of forced harmonic oscillator, or you can write driven harmonic oscillator, or it is can be written as driven harmonic oscillator, and corresponding differential equation and solution. You just put the heading this one. Okay. Now a particle which is applied an external periodic force to maintain oscillations in the resistive medium is called the forced harmonic oscillator, what we discussed. Let us consider a particle of mass m oscillating under an external force, that is your F equal to F0 sin pt. See, sin, cos, these are the periodic functions. So here we discuss that a applied force a periodic. So any force or any equation, if it is represented by sine or cosine, that means that is a periodic one. Okay. So here external force F, if periodic, then it can be easily represented with the help of sine and cosine function. Here it is represented by F0 sin pt, having the amplitude of F0, here it is written of amplitude F0, and frequency is p by 2 pi, because you can remember sin omega t, for sin omega t, omega is equal to how much? 2 pi by t. Okay, or omega equal to 2 pi by t, or 2 pi into f, and f equal to omega by 2 pi, right? The so called frequency is omega by 2 pi. So here instead of omega, if we are going to write p, then obviously frequency will be p by 2 pi, whatever written over here, and frequency is p by 2 pi. Okay. The forces acting on the forced harmonic oscillator is given by restoring force, that is minus kx, where x is displacement, k is force constant of the oscillator. Now damping force also proportional to the velocity, whatever we have been already discussed at the time of damped harmonic oscillation. that is your minus gamma dx by dt, which is proportional to the velocity, that is minus gamma dx by dt, and gamma is a constant called damping coefficient, and external periodic force is F0 sin pt. So whenever the body is oscillating in a resistive medium, then what type of force, if you are going to consider only, suppose this is the particle oscillating in the resistive medium, air medium, suppose air medium, the two forces is going to be automatically will be found on this oscillator, that will be, one is restoring force, that is minus kx, and another will be the damping force, that is, which is proportional to the velocity, is nothing but gamma dx by dt. If we are going to consider the damped harmonic oscillation, but in case of forced harmonic oscillation, another force which is applied externally on this oscillator, that will be represented by F0 sin pt. So in case of forced harmonic oscillation, three forces will be come into the picture, that will be your restoring force, another is damping force, another is external force, three forces. Okay, so now we are going to write the equation, differential equation, which represents the dynamics of the forced harmonic oscillation. So the equation of motion for forced oscillator is given by applying by considering Newton's second law. You just write by considering Newton's second law, which is force equal to m into a, mass into acceleration. Okay, so m into a, that is, you can see m into acceleration can be represented by the double derivative of displacement d square x by dt square. These things already we have been discussed whenever we have been at the initial of our discussion. You can see for the differential equation of simple harmonic motion, same thing we have been discussed. For damped harmonic oscillator also we discussed the same thing, that force is considered as a can be written as d square x by dt square, whatever written over here is equal to all the forces, that will be minus kx is your restoring force, minus gamma dx by dt is your damping force, plus F0 sin pt, which is the external force. Take these two terms to the left side, you can found this one, m d square x by dt square plus gamma dx by dt plus kx equal to F0 sin pt. Okay, that implies d square x by dt square plus gamma by m dx by dt plus k by m. Just I divided m with each term, then I can found gamma by m dx by dt plus k by m dx equal to F0 by m sin pt. Let it is your equation number 1. Now we have to put gamma by m equal to 2b, let it is your equation number 2. K by m equal to omega square, let it is equation number 3. F0 by m equal to F0, small f0 is equal to 4, equation number 4. So we have to put these things over here. Okay, using these values in equation number 1, we get d square x by dt square plus 2b dx by dt plus omega square x equal to F0 sin pt. Let it is equation number 5. So equation number 5 is the differential equation of the forced harmonic oscillator. Again, I am going to be tell to you one thing you have to remember always, whenever you can found a differential equation, that differential equation says, or the physics behind any differential equation is a dynamics, in your surrounding. I can say like force is equal simple, force is equal to, or I can say acceleration a equal to 5 suppose, the body is moving with a acceleration a equal to 5, that means d square x by dt square minus 5 equal to 0. If this differential equation you can found, then you can just imagine that a body is accelerating with a with the value of 5. Suppose likewise also means if acceleration is there, means there will be a force. So, or you can imagine a body is accelerating in a field, in a force field like that. So, a second order differential equation means there will be a dynamics of a particle with respect to something. Okay, so second order differential equation, wherever you can found, this represents some dynamics in your physics. Okay, so the complete solution is given by the sum of complementary solution and particular solution. See, complementary solution and particular solution, about this detail, in detail you can study, you are going to be study in your core paper 1 in this semester. In your first semester core paper 1 you are going to study complementary solution function and particular solution in your differential equation mathematical physics paper. Okay, so here I want to recall one thing, that you just go back for damped harmonic oscillation. We found this differential equation. How we solved? We considered its auxiliary equation, right, and we got the two roots, and then we considered its Wronskian, and we written its solution, general solution. This general solution also called as the complementary solution. Okay, so in this case differential equation is something in left hand side is the second order differential equation is equal to 0. So for this differential equation we can find only complementary function or solution, but here in this case differential equation is somewhat different. That means left hand side we have differential form. In the differential form here d square x by dt square dx by dt is there. In the right hand side another sine function. So if we are going to solve this equation, first we have to consider 0, this much equal to 0, we can found the complementary function, and we are going to consider this one for particular solution. Means I can say that in detail you are going to study in your core paper 1. So I just applied the concept over here. You just follow this. Some other day I will be do a solution of this type of differential equation for you. Okay. So you just accept here that if this type of differential equation we have, then we can found the general solution will be the sum of complementary solution and particular solution, or complementary function and particular solution will be written as xt equal to x1 plus x2. x1 is your complementary function, x2 is your particular solution. Okay. Now first we have to consider the complementary function or the transient state. Here transient state means damped harmonic state. Okay, you can say your damped harmonic state, because you just think that a oscillator is oscillating like this. Okay, that means if there is no force, it is goes on decreasing its amplitude and coming to the rest. But at the meantime, if I am going to apply the force, that means the amplitude is decreasing due to the resistive nature. At the meantime, this oscillator acquiring or taking the frequency of outside force. So that means this is the situation from which it transit, means transit its original position to another situation, original frequency to another frequency, transition. Due to transition of its originality to another, only for that it is called the transient state. Okay, so at the end of this state, this oscillator's frequency, natural frequency, will be transit to the frequency of applied force. Only for that it is written as transient state, right? Okay. So d square x by dt square plus 2b dx by dt plus omega square x equal to 0. Let it is equation number 6. The solution as obtained in damped harmonic oscillator case, because already we have been solved in our previous topic, we no need to solve in detail. Direct I have to write the solution. That will be x1 equal to a e to the minus bt sin bt plus phi. Let it is equation number 7. I can show you. You have already found that answer. See, this is xt equal to a e to the minus bt sin beta t plus phi. In the case of damping case means natural frequency is greater than that of the resistive nature of the medium. So here beta is nothing but omega square minus b square root over, and the amplitude here a, this is a, not a0. Okay, this is a, not a0. A e to the power minus bt. I have to write one second, a only. Okay, a e to the minus bt sin beta t plus phi. Here beta is equal to omega square minus b square root over. Omega is the natural frequency of the particle. B is the resistive part of the medium. Resistive part or resistive nature, you can say resistive nature of the medium. And the amplitude a to the power minus bt is the amplitude which is decays or decreasing, continuously decreasing with the function of exponential. Because see, this is e to the minus, means this amplitude decreasing exponential with time, and the motion therefore after sufficiently long time dies down. So this state is called as the transient state, because I just before I explained that as it is its amplitude decreasing with time, so this state is tends to, or it is the state from which it is transit from its the so called damped harmonic oscillation to forced harmonic oscillation. And here we have to stop our today's discussion. Next class we are going to start to discuss this much, that is your steady state. Okay, so thank you so much for watching this video. Thank you. You go for this video perfectly and write down the note in detail, and if you got any doubt, you ask with you discuss, you ask me, contact me, we are going to discuss. Okay, so thank you so much for watching this video. Thank you.